So hi, I would like to solve an example from the exercises in the OT class. I would like to solve an boost converter example. So in the question we have a boost converter. Again, this is a typical boost converter in figure, so you don't have to worry. And our input voltage is 20 volt, our duty cycle is 0.6, and we have a load of 12.5 ohms. And L is 10 microhenry and C is 40 microfarad. Okay, and the switching is 200 kilohertz. First we need to find the output voltage, then we need to find the average maximum and minimum of the inductor current, and same for the voltage ripple and diode currents. Okay, so let's try to draw the equivalent circuit first. So let me draw it here. So in a boost converter we have the inductor connected like that, right? So then here we have a diode, and then we have a capacitor, and our load resistance is connected to here, so that is 12.5 ohm. L is equal to 10 microhenry, and this is our VL, and this will be our V. Right, so the first question the first part asks about the output voltage, and we know from the equations, and again we will prove that, but V out is like V in divided by 1 minus D. So as the D gets bigger, so we will have a higher output voltage. So if we just put those things in place, so that is 20 volts. So 20 divided by, and our duty cycle is 0.6. So 0.6 is for 60% of the time that switch is on or closed, and for 40% of the time it is off, right? So that is that duty cycle, and we will draw the voltage and current characteristics. So let me get rid of myself here, and it is 1 minus 0.6, so it is 20 divided 0.4, so I can have like 50 volts, right? So the output voltage is 50 volts under, steady state conditions. So actually I can calculate the output current here. So I out is equal to V out divided by R, so 50 divided by 12.5, that is 4 amps, right? So I have an output current of 4 amps, and it is flowing through 12.5 ohms, right? So let me write the other important parameters here, and I know our switching frequency, it is given here, it is 200 kilohertz. So in 1 second, okay, so in 1 second that switch is turned on and off as like 200,000 times. So it is really turned on and off really at fast speed. So our TS is equal to 1 over S. TS is the total period, so it is 1 over 200k. It is 5 microseconds. So 1 cycle is completed just in 5 microseconds. Okay, so first let's plot the voltage and current characteristics, but there's another important thing, and let's think we have like a black box. I mean, it's the same thing for buck converter or boost converter, and if we, in this course we are not interested in the losses in the converter. So from here, if it is giving out some output power, so we need to draw the same amount of power from the input, like assuming like that converter is 100% efficient. I assume it is like 100% efficient because now I assume like an ideal inductor, and I assume an ideal switch, ideal diode, and ideal capacitor. And remember, only resistive components dissipate heat. Of course, in in a real boost converter application that has some resistive components and diodes and switches has some conducting and switching losses. But anyway, so if this is I out and if this is V out, so if this is I in and if there is like V in, so for every converter input power should be equal to output power. I mean, because if let's say we are increasing the voltage, okay, if we are increasing the voltage and if we just let's say if this is like 4 amps getting out, so it is 50 times 4, 200 watts is supplied. But if we draw 4 amps from the input, so that just makes like 80 watts. So 80 watts coming in and 200 watts going out. So that's not, you know, possible. So we need to calculate the input current. So actually it's like the inverse of the relation of the voltage ratio, as you can guess. But anyway, let's write it. So 20 times input current is equal to, sorry, so okay, and the output, I know it is like 50 volts and the output current is 4 amps, so it is 200 watts. So my input current should be 10 amps, right? So actually, you know, that is one important thing about boost converters. Yes, we are increasing the voltage level, so we are increasing voltage from 20 volts to 50 volts, but that energy is not coming from nowhere. So it is not like we are keeping the current same and increasing the voltage, you know, from nowhere. So we are increasing the voltage, but we are sacrificing the current. So the total input power is 200 watts, 20 times 10, and our total output power is still 200 watts. I mean, again, in a practical boost converter, there will be some losses in those components, but again, even in like practical boost converters, the efficiencies are like well above 90%, 95%. So the losses are still minimal. Anyway, so the question is like how does it work? So we draw like 10 amps in average. Again, this is not the constant voltage, not constant current. So this is an average current, and there will be some ripple on the inductor. So again, let's try to find the average, maximum and minimum inductor currents. Okay, so let's try to plot the voltage characteristics. So let me draw a couple of coordinate systems here. Right, and let's put it here. Okay, so let's say the first one is VL and the second one is IL, right? We'll draw that part here as well. Right. So when the switch is on, when it is, when the switch is on, it is closed here. So VL during switch is on, or during D times TS, VL will be equal to input voltage, right? So I can write VL is, let's say each of those things are like 10 volts. So okay, so this is 20 volts. So switch on, VL is equal V, like for how long, D time TS, right? And this is put here. Okay, and what I know is if, I mean, you can write here, so VL is equal L di over dt, and if you apply a positive voltage to the inductor, basically the current will increase linearly, right? So let me try to draw it here. So let's say it is going from here to somewhere here, right? So again, that instant is t on, and t on is equal to b time ts. Right, so when the switch is off, so it is for 1 minus d time ts, right? So in that instant, let me use the red one. So I open the switch, turn off it, and VL will be V in minus V out. Sorry, I think that should be not V in, that should be V out, of course. Okay. So for when the switch is off, VL is equal V in minus V out, and it is 20 minus 50, that is minus 30 volts. So let me draw it here. It just comes down to here, something like that, right? And then it will start again. So here it is minus 30 volts. Okay, so again, if you are applying a negative voltage, then that thing will discharge, and the idea, like all the assumptions we made, is if, let's say, that area is, let's check it, and you can have, let's say this is area A, and let's say that is area B. So in this case, again, this is how we define to have like steady state conditions, because what we know, again, I mean, you can write that equation as like I at t is equal to 1 over L 0 to t VL dt plus the initial current, right? Or you can bring it here, I t minus I0 is equal 1 over L 0 to t VL t dt, right? So if that one is 0, which is the assumption for the steady state, so I start with some current and I end up here, then I start the same cycle again, so it just goes on and off. So that means the integral of that thing should be 0. So the integral of that thing being 0 means area A, orange area, is equal to B. So again, you can quickly double check, and actually that is how we derive the voltage characteristics of the boost converter. So 20 times, let me do it here, so A is equal B, so that is 20 times 0.6 times TS is equal to 30 times 0.4 times TS. So this is 1 minus D TS, right? So again, this is, TS can be cancelled. 120 is equal to 120. Sorry, 12 is equal to 12, right? So they are equal. But then the question is how we can calculate the average and the minimum and maximum. So this is the minimum inductor current, so this is the maximum inductor current, okay? And between these ones I have delta I L, let's say. Okay, so how can I calculate that one? Actually, that can be calculated either from TS or from 1 minus dTs, because I know the ramp. I can calculate the slope, or I can get the voltage. So let's use the on period, right? So for that one, let me write again. I will use that equation, but from 0 to T on. T on is here, right? So I can write I at T on minus I at 0, which gives the delta IL here, and it is 1 over L, 0 to T on VL T dt. And I can write it like that. So I know the voltage. So VL is V in during that time. Okay, and the integral is the period, or T on is equal to D time TS divided by L. Okay, let me put those things in place. So input is like 20 volts, our duty cycle is 0.6, and our TS was 5 microseconds. Okay, 5 microseconds, and L was it was given in the question, it was 10 microhenry, right? And actually, you can easily calculate it, and you can find that one as 6 amps, right? So from minimum to maximum, there is a difference of 6 amps from that one. Actually, you can double check using the other calculation here. It should give us exactly the same characteristics. Okay, so I know the difference is 6 amp. So, but how does it work? Like, is it go from 4 amps to 10 amps, or it go from 10 amps to 16 amps? So how can I find the average value? So let me draw it here. So here it is the average current. I mean, this was again IL. Okay, this was the inductor current, but there's interesting thing. It's not like that in the buck converter, but it is here. So if this is IL, I can say IL, inductor current, is equal to input current, because there's no other way for input current to flow. So when the inductor current is 5 amps, the source current is again 5 amps. So we already calculated what should be the average value of our input current, so that is equal to inductance current. So let me draw it from scratch. Okay, so again, let me draw a couple of coordinates. Let me draw them larger now. Okay, so let's say that is IL, and let's say it is going from here. Now I'm trying to put it to the scale. So somewhere here, right? I will tell you why I put it like that. Okay, so if let me draw those things again. And this is our minimum current, and that is our maximum current, right? And I know that distance, okay, is equal to 6 amps, and I know the average current somewhere here, okay, so that is our average current, and this is equal to 10 amps. All right, and again from geometry, you can use those tricks, like those ones. Okay, so basically that area is equal to here, that one is equal to here, symmetrical. So you can say I max is equal to I average plus delta I divided by 2, and minimum current is equal to average minus delta I divided by 2. So average was 10 amps plus 6 over 2, so that is 13 amps, and that one 10 minus 6 over 2, that is 7 amps. So that is 7 amps, and that is 13 amps, right? So we are seeing from our input voltage source, when you just turn on that switch, again we are not here, we are not dealing what happens if we just start when the inductor current is 0. That's a problem we investigate in the 4th year power electronic course, but in this course we just assume the steady state operating conditions, right? And in the steady state conditions, we assume you started the converter and it's already working under steady state conditions, and the steady state conditions for that boost converter starts from 7 amps. You close the switch and it starts climbing up because we are basically short circuiting the inductor, and once it reaches to 13 amps we turn off that switch, and that 13 amps is being charging the capacitors and the load. Then when it's dropped to 7 amps, then we just turn it on again. So you have that kind of waveforms going on and on continuously. So the next question, again, I will calculate the output voltage ripple, and that one again is not included in the exam. You are not responsible for that one, but for those who are interested, I will solve it. But let's calculate the average diode current. Okay, if this is the diode current, draw it here. So what's happening is you have the diode current here, you have the capacitor current here, and you have the output current here. So whenever that diode current is larger than your output current, the extra current charges the capacitor, right? And whenever the current coming from the diode is less than the output current, then the capacitor will be supplying the load. And again, in the steady state, the amount of charge going into the capacitor and the amount of charge going out of the capacitor should be equal to each other, so the output voltage can stay at a constant voltage. Okay, so let's try to calculate ID. Actually, ID, when the switch is on, when it is charging here, ID will be 0 because it is at reverse conducting. There's like 50 volts here, but that node is like 0 volts because that switch is on. So it's 0 volts here, 50 volts here, there can be no current. So whenever the switch is on, diode current is 0, and whenever the switch is off, then that inductor current has nowhere to flow, and IL will be equal to ID. So let's write here. So when the switch is on, so this is the diode current, okay, ID diode current. So when switch is on, and in that instant diode is off, and if this is off, ID will be 0, and when switch is off, diode will be conducting and ID will be equal to IL. So let me try to put those things here, and whenever the switch is on, whenever the inductor is charging, our diode current will be 0, then it will be exactly the same thing, okay. So let me draw here somewhere here. So each square is like 2 amps. So I will try to make it realistic. So then it will exactly be that shape, right? Then it will come down to 7 amps somewhere here. Then it will be exactly that shape. So we are just omitting the positive, increasing or DTS part, but whenever the switch is off, so for again 1 minus DTS, so our inductor current, the diode current will be again from 13 amps to 6 amps. Okay, so that is our second leg. Then what is my output current? Output current is constant 4 amps. So it will be like 4 amps going on here. So whenever ID is larger than 4 amps, it will charge the inductor. Whenever it is less, the inductor the capacitor will discharge. So let me draw, I don't know, let's make it orange again. So it is somewhere here, right? So that one is I out, that is equal to 4 amps. 4 amps. So whenever your inductor current is larger than that one, so let's draw here. So here, so C is charging, and here C is discharging. Okay, and again, if we want to have if we would like to have constant capacitor voltage, and if it is operating under steady state conditions, again we have the same trick here. So you can have that area, and let's call that delta Q, because if you integrate the current, you will find columns or the charge, and this is, let's say, minus delta Q, right? So delta Q, or let's say let's call that one delta Q 1, and this is delta Q 2, and basically delta Q1 is equal to delta Q3. Okay, they should be equal to each other. Okay, so before getting into that calculation, let's see, first let's see what is the average inductor current. Okay, so let's double check. Let me get it off here. So average inductor current. So it is IL average is equal to 1 over T 0 to T IL. So it is, we can calculate the area under that shape, and you can, divide by TS. All right. So let's try to calculate that one. Again, actually you can just, use the geometry, and you can say, that area of the triangle is equal to that area of the triangle, and that area is equal to that area. So you can put here. So you already see that is equal to 10 amps, and that is actually how we prove the other one, how we prove the power flow. But let's calculate the average diode current, right? So average diode current, ID average 1 over T 0 to T ID T dt, right? So it is 0 here, okay, it is 0 here. Then I need to calculate, that area, and that is 13 amps. And how can I calculate the area of that trapezoidal shape? It is 13 plus 7 divided by 2, it is here, times 1 minus D, it is 0.4 times TS divided by our period is TS, so you don't have to worry about TS at all. So 20 divided by 2, 10 times 0.4, it is 4 amps. I mean, it is what we expect, right? It is equal to output current, because on average I should give enough current flow here, and I can give like 4 amps from the output. Sometimes I am giving more currents, but sometimes I am not giving no current at all. But in average that is equal to 4 amps. So in that way, the amount of charge getting into the capacitor and the amount of charge getting out of the capacitor, they are equal, right? So this is an important feature. So then let's calculate those ones. And again, the selection of the capacitor charge, the selection of the capacitor size is totally dependent on that one. There is not like a certain rule, but if you want a high quality boost converter, you can put a large capacitor size. You can have like really minimum voltage ripple, but sometimes the volume is limited, or the cost, there are some constraints on the maximum cost of the converter. So you want to put some, you want to reduce the cost of the capacitor, so you choose a smaller size. So let's calculate the ripple. So what I know is here it is charging, right? And whenever it is less than that current, it is discharging. So these two are equal. Again, voltage is increasing sometimes, and sometimes it is reducing. So actually, if I just assume to reach the minimum voltage at the end of discharging, then at the end of that cycle I reach the maximum capacitor voltage. And how can I calculate the change? Okay, it is simple. So again, charge is capacitance charge voltage, and you can calculate that one like divided by C. Okay, and let's calculate the total charge here. So here I have to calculate not all area, but I have to calculate just this area. Or again, you can calculate here, and actually let's calculate both of them and show they are equal to each other, right? So delta Q1 is equal to, again, this is sorry, I think this should be not 6 amps, this should be 7 amps. The distance was 6 amps. Anyway, so here I want to calculate that orange area. so it is 3, okay, it is 3 here, and it is 10, sorry, 9 amps here, okay, 9 divided by 2, okay, times 1 minus d time ts, okay. So again it is 6 times 0.4 times 5 microsecond, and it is 12 microcoulomb, okay. That area is 12 microcoulomb. So let's calculate the Q2, okay, here. So it is easier because it's like constant charge. So it is 4, times, it is d times ts, or 0.6 times, let me write in total 4 ts, it is 4 times 0.6 times 5 microsecond, and again it is 12 microcoulomb, okay. They are equal to each other, okay. Then I can calculate that voltage ripple delta V is equal to delta Q, one of them, divided by C, and C, like it is giving the exam, giving the question like 40 microfarad, right? So it is 12 microcoulomb divided by 40 microfarad, and it is 0.3 volts. So the output voltage is 50 volts, and our ripple voltage is 0.3 volts. So actually the output voltage is like 50 plus minus 0.15 volts, okay. Again, if you think it is like 3% ripple, so again it can be negligible, and that is why during charging time we assume like that voltage to be constant, and the inductor is charged or discharged linearly, okay. But if you want to really calculate the real waveforms, it is a second order differential equation, but we are not interested. And actually numerically, even if you do it like accurately, there's not much difference, okay. So that is the all I would like to say about boost converter. So be careful about the output current levels. So the amount of current sent from the output is not equal to the current drawn from the supply, and the excess amount of current is being used to charge the capacitor, so that it can use that extra charge to supply the load. Because during that time, when you are charging your inductor, basically capacitor is just by itself supplying the load, okay. So I hope that is helpful. Thank you.